Hello everyone, today we're gonna solve the unique binary trees 2. This problem gives us a number n and we need to return all the unique BST binary search trees, which exactly n numbers of unique values from 1 to n, and we can return it in any order. So if we have n equal to 3, we're gonna have the 4 cases, and now let's consider a smaller tree. For example, if we consider n equal to 1, so which means that we have a tree with just one node, and with n is 2, we're gonna have these 3 cases. I mean 2 cases. And the question we should ask ourselves is that how do we create the binary search tree with n equal to 3? And um, a way to think about it is that we can construct the n equal to 3 from the previous case. For example, we already have the tree with n equal to 2 with 2 nodes, and now we need to build 3 nodes binary search tree. We can basically insert the node, the n equal to 3 equal to this place, right? So basically we can just insert node right here, right? And we're gonna do this. Right? Basically we can just connect the node 3 to the previous 2 nodes binary search tree to the left side, and we're gonna do the same thing right here. We're gonna just connect connect 3 with 1, and that's all for our 3 nodes. But if we insert it as a root, we're gonna lose 2 cases, this case and this case and this case as well. So we're gonna lose 3 cases. And for these 3 cases, how can we construct these 3? So the answer is we can also build from our 2 cases approach. So basically, in this case, we're gonna try to insert 3 after the node 1, and we're gonna try to insert node 3 after the node 2. So for example, let's say we already finished all these 3 cases, all the 2 cases, and I'm gonna just erase that. And now we're gonna try to insert behind 1 and insert behind 2 here. Now insert behind 1. How can we insert behind 1? And behind 1. How can we do that? So what we're gonna do is that we're gonna replace the current connection with the connection of 3 to this, and then we will connect the 3 left to the current 2. So that's what we're gonna do to create this case. And to insert behind 2, let's say now we're gonna insert behind 2. How can we do that? So we're gonna also have 2 cases. Yes. And let's say let's try to insert 3 behind 1 in this case. Do we Can we insert 3 behind 1 right here? The answer is no, because if we insert 3 like this or like this, obviously the node from the root node is 2, right? So we have to make sure that all of the value in the left subtree gonna be less than the root node. So right now we have n equal to 3 greater than 2, so we cannot insert to this current tree. So this case doesn't exist, right? So we already handle this case and these two cases, and now we're gonna try to insert 3 behind 2 to handle these two cases. And now to insert 3 behind 2, so what we're gonna do is basically if we see that the right side of the node 2 doesn't have anything, so we can just insert 3 right here, and we're gonna do the same thing right here. So that's basically the idea. We will try to insert the n node from n minus 1 substrees, and we have two cases. We insert n as a root node, or we will insert n behind 1 to n minus 1. So basically we have cases just insert n as root, and we have another case to just n behind I with I equal to 1 to n minus. And we need to careful about the case when we cannot insert 3 into, for example, behind 1 in this case. Cannot do that, so we need to careful about this case, right? That's all for our approach. And now let's jump into the coding part. So we will consider the edge cases as usual, right? Edge cases we have n equal to 1, n equal to 2, let's say n equal to 0. So if n equal to 0, basically we're gonna return the vector, and if n equal to 1, we're gonna return a just one node vector. We're gonna have a vector p node star with just new node 1. That's for one node. And now we're gonna use a backtracking approach right here. We're gonna have a vector node current subtree gonna be equal to generate all the tree to n minus 1 node. And then we're gonna look through all of the subtree. This one, we're gonna look through nodes tree in our subtree, right? And then we're gonna, first of all, we're gonna need to duplicate it before we modify it, so that we have the correct memory. So let's say we have a duplicate tree, and then we're gonna just connect n to order tree as a root, right? So how can we do that? Basically, we're gonna have a new tree gonna be equal to a new tree node of the value n and our current tree, and with the right one is a new pointer. So that's basically we connect n right here with our current subtree, and then with the right node is a null pointer node. So that's the idea. Then we need to store the new tree. Let's say we have a vector result like this, and then we need to store the tree node. Have dot pushback or new tree. That's basically yeah. And for duplicate function, it is tree node, tree a root node, and we're gonna return a tree. Well, that's duplicate function. Then now we will create new tree by adding n after or behind a position. So we're gonna do the same thing right here. We're gonna look through all of the subtree, and we're gonna create a new current tree. I duplicate it as well. Then we will modify the current tree, and we're gonna insert after I equal to 1 and minus 1. For I equal 1 and I less than n is I. Then we're gonna insert I with n with the current subtree. If we can't do that, we will push back the current subtree to our result, and then we're gonna duplicate it again. Excuse me. Then we will write a function to insert behind with the current tree, and we need to insert n. Perfect. And now we're gonna write these two functions. First of all, we're gonna need to write a duplicate function. So first of all, we're gonna need to create the new head first. So step 1, we need to create a new head. So we have a new head equal to most head dot value, and then after that we're gonna duplicate the left node and right node. So basically we're gonna need to double check whether or not if our one is if we have root left different with the pointer, we gonna have new root or new head left go to it of root left and do more right node. Get right, and finally we just gonna turn new head right here. Perfect. And to insert behind, we need to consider, first of all, we need to consider whether or not our current tree is a null pointer or not. If it's a null pointer, we just need to return false here. And then we're gonna consider our current tree values to see whether or not is the one we need to insert behind. And then we just need to insert and to the right side behind I. So basically we're gonna consider if the current right is a null pointer. It's easy, we just need to assign the current right should be equal to new node and else if we already have the right side, what we're gonna do is we're gonna break the connection right here. So from this, right, we're gonna create this. So basically we're gonna break this connection and connect to 3 and connect to connect to 2 again. So how can we do that? First of all, we're gonna have a new current height pointer. Then we're gonna assign the current right to our new tree node. And then we're gonna connect the new node left to our previous current right? So one is current right, it's gonna be easier to figure out. Okay, current right and pointer. And if we can do that, we will return 2 right here. And else, if we don't have the current tree value equal to I, we're gonna need to search for it. So if we have the current value greater than I, if we have the current value greater than I, which means that it's gonna be in the case where we have 3 right here, right? And when we consider this case, if we have 3 like this, less than, let's say if the current value is greater than I, right? We're gonna need to move to the left side, right? So we cannot do that. So that this one we're gonna just return false right here. Because for example, if we have I equal to 3 and the current value equal to 4, right? And then you have 4 right here, 2, 3, like this. So we cannot insert anything below 3 in this case, so that's why we're gonna return false right here. And else we're gonna just need to move to we just need to return the insert behind and we need to move to the current right. This one is we have the current value is less than 1, less than I. So that's basically the idea. And we already covered all the cases, but for the sake of the compiler, we just need to return whatever is it right here. Maybe just return right here. That's all for the implementation. And The time complexity for this one obviously is O to the power of n, and the space complexity is gonna be the same thing. And then the topic for this one is backtracking, cost, back, and tree, and binary search tree, and DFS. Well, that's all for this problem. Hey, this one current order so vector or perfect. And finally, we're gonna need to return the result here. Right, good to me. All right, we will resolve this problem. And if you have any question about this problem, just leave it below, and I will try to answer all of them. Thank you, and hope you guys enjoy it.